Good morning, everyone. So today we are going to talk about a few related topics all around response of dynamic systems. So let's start by finding steady state response of dynamic systems from their state space model. So far we have found, if you recall, steady state response from differential equations. The approach there was to drop every term that had a time differential on it to zero so we can find steady state response. We also introduced a theorem called final value theorem for finding a steady state response from transfer functions. This is the last type of model. The third type is a state space model. So the question is, if I have the state space model of a system, which means I have matrices A, B, C, and D, can I find Y steady state? Can I find Y, the output of the system in steady state, if I know the input to the system? And the answer is yes, and it's very similar to the approach we took when we found steady state responsive system from their differential equation model. If you look closely at the first part of a state space model, you would see a series of first order differential equations. X dot is equal to ax plus bu. So in steady state, that dot term has to be equal to 0, which is what we show here in this line. So if we call the first portion of the state space model equation 1 here, from equation 1, you set the dot term equal to 0, which will give you a 0 for the left side of the equation. So 0 is equal to a times x, but not every x. This is x at steady state. So the value of state variables or state vector in steady state plus bu, whatever that input is. So that's one equation we have. So from there, you can find x steady state. So it is ax plus bu. You will take ax to one side. So ax steady state. We usually put an underline to indicate that this is a vector. If you take it to one side, this will have a negative sign, and this is going to be equal to b times u. So a times x steady state is equal to b times u. So we want to find x steady state. So what do? You have a times x equals b times u, and you want x. What do? Our natural tendency is to divide by a, by coefficient a. But because we are dealing with matrices, instead of dividing, we pre-multiply the whole equation by inverse of the matrix that we want to get rid of, by inverse of the matrix. So in other words, you take this equation and multiply a inverse by both sides of the equation. So this becomes minus a inverse times a times x steady state is equal to a inverse times b times u. So a inverse and a cancel each other. So what will be left is this. So you will arrive at this equation that x steady state as a vector is equal to minus a inverse times b times u. Now the negative, you just multiply both sides by a -1. And we can do it in this state, so our answer would be consistent. So if you multiply both sides by a -1, you will arrive at x steady state is equal to minus a inverse times b times u. And you have everything that you need to find x steady state. A is known, b is known, and so is u, the input to the system. Now, once you have x steady state, the next step is to plug it into equation 2, which is the second part of our steady state model. So second part of our state space model. So you take this and plug it into equation 2, which will give you y steady state is equal to cx steady state plus du. And we already know what x steady state is, so we are going to plug it in. So c times a inverse times b plus d, the quantity times u. So based on that, we can find steady state response of systems with a state space model. So let's solve an example. So the example would be this second order system. So we are going to find, I'm going to give you a minute. You already know the state space model of this system. Go back through your notes and find A, B, C, D matrices for this system. I'm giving you this the differential equation, and I'm asking you to convert that to a state space model. And once you have the state space model, go ahead and find the steady state output to a unit step input. So if the input is u equals 1 at time 0, what would be the output of the system in steady state? Okay, in order to set up our state space model, we need to um, recognize and define the state vector, which would be made of position and and velocity, the output which we choose to be displacement, and the input is u. Understanding that if it is representing a mass damper spring system, u is of unit force divided by mass. So u, what you see on the right-hand side, is force divided by mass. So in order to find the matrices, you need to form the first portion of the state space model. The typical first row is 0, 1, stating that the derivative of x1 is equal to x2. So derivative of x1 is x dot, which is equal to x2. So 0, 1 shows that. And in that equation, there is no u, so this is 0. For the second row, we are essentially saying what x double dot is in terms of x and x dot. So minus omega n squared is multiplied by x, minus 2 zeta omega n is multiplied by x dot, and 1 is multiplied by u. So we have matrices A and B, and to basically say y is equal to x, 1, 0 needs to be multiplied by x plus 0 times u. So our d is equal to 0. So if u is 1, and to show that it's a unit step input, the way to show that this is 1, but it's 1 that comes on at time 0, not any time before 0, you include a pair of parentheses and say it comes on at time 0. To be accurate, this is really this. This is t minus 0. So what does this say? It says your input, if you plot it versus time, so if this is u versus time, is this time function. So it's 0, before time 0, and it goes to 1 and stays on for the rest of time. So this value is 1. So this is a unit step input that comes on at time 0. And while we are at it, let me explain another possibility. What if you want to show a unit step that comes on at 5 seconds? How do you show it? A unit step that comes on at times 5 seconds is shown like that. So a unit step that comes on at time 1 second, 5 second rather, is shown as 1 multiplied by t minus 5. So this function has still value of 1, but instead of coming on at time 0, it comes on at time 5. So similarly, this is 0 all the way until 5 seconds, and then it comes on and stays on as 1. So this is a unit step that comes on at 5 seconds. So this is 5 seconds. So it was a little bit of further explanation about unit steps. So what we're after really is steady state response. Yes, sir.
In your unit state space model,
Mm-hmm.
for the u value, that's 0, 1.
Mm-hmm.
Can you just explain real quick how you got that 1?
This one here, this one here.
Yes.
I'm sorry. This one.
Yep.
Okay. This comes here from this one.
Okay, just whatever's in front of you.
Yes. 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 So yeah. So this is a matrix multiplication, which means in order to find this second row, you multiply this row by the column. So minus omega n squared gets multiplied by x right here. Minus 2 zeta omega n gets multiplied by x dot, and the result gets added together. And this result gets added to multiplication of 1 by u, which is what you have here. And the reason we have 0 here is what? Because in the equation for x dot simply is equal to x dot without any u in it. So that's why it's 0. Okay, so let's go ahead and apply. Any other questions? Okay, so what do we need in order to find y steady state? I need to find A inverse. See, look at the equation. I need to find A inverse pre-multiplied by C and post-multiplied by B. So let's go ahead and find A inverse. Do you remember how to find inverse of 2 by 2 matrices? You have till tomorrow to learn. If you haven't memorized that. So A inverse would be okay, so what happens? The diagonal terms switch place, and the off-diagonal terms switch their sign. So, okay, so this therefore minus 2 zeta omega n comes here, and this stays in place, but it becomes positive omega n squared. This becomes negative 1, and this becomes 0. And this matrix should be divided by what? By the determinant of the original matrix. So in order to find the determinant, again, you multiplied 0 by minus 2 zeta omega n, which is 0, and subtract from it the multiplication of off-diagonal terms. So what is left as the determinant is omega n squared. So let me write this down. The determinant of A is going to be equal to omega n squared with the positive sign. So we divided that. So this is A inverse. To make it easier to carry forward with this matrix, I'm going to divide every term by omega n squared. So this becomes minus 2 zeta divided by omega minus 1 over omega n squared 1 0. So now we don't have to have the division line going forward. Okay, so this is A inverse. Going back to the formula, what do I need to do? I need to pre-multiply this by C and post-multiply it by D. So pre-multiplied by C means, so let's go ahead and find and multiply C by A inverse. C was 1, 0. And I'm not going to repeat A inverse. It's right here. So let's go ahead. So what is the expected dimension of C times A inverse? How many rows, how many columns in the resulting matrix? C is 1 by 2. A inverse is 2 by 2. So the resulting matrix would be? So this is 1 by 2. This is 2 by 2. So we said the way to find is to drop these two that are next to each other, and the dimensions from outside will define the final dimension. So the result would be 1 by 2. So take 1, 0, this row, and multiply it by the first column. So what is left is minus 2 zeta divided by omega n. And again, this for the second column. So what is left from the second column is minus 1 divided by omega n squared. So this is the result of multiplying C by A inverse. Then the next step is to take C times A inverse and post multiply that by matrix B. So I'm going to write it simply as C times A inverse. But B was what? B was 0, 1. Okay, so C times A inverse is 1 by 2. So C times A inverse is 1 by 2. B is 2 by 1. What is the expected dimension of the resulting matrix? So this is 1 by 2. And this is 2 by 1. So what will you get? Which means what? You get a number. You no longer have a matrix. So let's go ahead and multiply. So this is a row multiplied by this column. So this gets multiplied by 0 and the second by 1. So what is left is minus 1 divided by omega n squared. Okay, so if you go back to the formula for y steady state, there is a negative 1. There is a negative sign rather that is multiplied by C times A inverse times B. So if you multiply, if you incorporate that negative sign, and D by the way is 0. So y steady state is minus C A inverse B plus D times U. So D is 0, so what is left to do is to pre-multiply it by a negative sign. So y steady state therefore is equal to, and U is 1, so y steady state is 1 over omega n squared. And if you look at the differential equation, everybody, look at the differential equation. If you drop all the dot terms, what you will get is omega n squared times x is equal to u. If u is equal to 1, that means x steady state is 1 equal to omega n squared. Can you see that? So from the differential equation in steady state, what you have is omega n squared x steady state is equal to u. So if u is 1 for a unit step, that gives you that x steady state. Here, x steady state is position. And the way you can tell is that there is no underline. So it's a scalar, is 1 over omega n squared, which is what we found here. And if you do the same thing for a transfer function of the exact same system, you'll find the exact same answer. Any questions before we go forward? Okay, there are a number of other examples. This is one of them. So I leave this for you to solve. And because this is a fourth order system, the resulting A matrix would be 4 by 4. So in order to find inverse of a 4 by 4 matrix, you need to probably use a calculator or something like MATLAB. So this is something that you need to have a tool to perform. Okay, so far we talked about the fact that the transient portion of response of dynamic systems, the nature of the transient response is defined by location of poles. I showed you a picture where by knowing the location of poles, you can tell how the transient response looks like. And we talked about it in the context of a familiar system, which was a second order system. You remember we talked about damping ratios, and as damping ratios changed, how the location of the two poles of the system changed. So that was a confirmation for the general idea that the location of poles of a transfer function defines the nature of the transient response. And the transient response was what? What was the definition of the transient response? Let me ask you in the middle. Do you remember the transient response? So that if you look at response of a system, let me see if I can quickly bring it up. So for example, this is not a bad example. So look at this. If this is response of a system, for a portion of time, for a span of time, this response is changing. This response is changing for a portion of time. That portion of response that is changing with time is called transient response. The portion of the response that it no longer changes with time is called steady state response. So in this example, therefore, this is steady state response, and this portion up to this point from time 0 to here, this is transient. Okay, so what are we saying? We are saying how this transient response looks like is defined by poles of the system. That's what we have. We are talking about. But you may ask me, okay, don't we have 3 different kinds of system models? We have, of course, the transfer function where it's easy to find poles. You take the denominator of the transfer function, set it equal to 0, and you find your poles. But what if you have a differential equation as the model of the system, or the state space model of the system? How do you find those values that will define or determine the transient nature of the response? And that's what we will going to discuss next. So when you talk about the differential equation, you can get similar information by finding roots of characteristic equation. From differential equation course, you may remember that if you have a differential equation that looks like that. So let's say it's a second order differential equation and it's x double dot plus 2x dot plus 5x equals u. So if you want to solve this differential equation, one method, which is called method of undetermined coefficients, basically says, I'm going to assume I know what the response is. I'm going to assume that x as a function of time, which is the response I'm after, is going to be an exponential function. So a times e to power lambda times t. So if I know a and lambda, I know my response. Look at this function. If a is known and lambda is known, I know what the response is. And it's an exponential function. So my mission now, from this time forward, is to find lambda. Okay, so how am I going to find lambda? I'm going to back to what I know. I know this is the differential equation of the system. So let me go, and in the differential equation, I have x dot and x double dot. So let me go ahead and find x dot. What would x dot of t be? If x is this, what is x dot? What is x dot? This is an exponential function. The coefficient stays. So it becomes a times, did you say lambda? E to power lambda t. Do you agree? How about x double dot? Quickly, x double dot is going to be what? A lambda squared. Exactly, a lambda squared e to power lambda t. Okay, so we know what x is, what x dot and x double dot are. So we're going to go back and plug them into this equation. Is that okay? So let's do that. So if I were to do this, I will get for x double dot, what will I get? I will get lambda squared. So there's an a. So let's do that. If you look closely, a and e to power lambda is repeated between these terms. So I'm going to keep that out. So I'm going to write a e to power lambda t out, and then multiply it for x double dot. I'll get lambda squared. For x dot, I have lambda, which is multiplied by 2, so plus 2 lambda. And for x, I don't have anything, but I'll have 5. So it equals plus 5 is equals u. Equals u. Okay? And again, this is a reminder, a differential equation has, the response of a differential equation, or the solution of a differential equation, has two parts. One is called homogeneous, the other one is called particular. Homogeneous means when u is equal to 0, which captures the effect of initial conditions, and particular means when u is non-zero. It's a known function. So if you're after homogeneous response, so homogeneous response means when u is 0, then what is left is that this characteristic equation has to be 0. Lambda squared plus 2 lambda plus 5 has to be equal to 0. Why? Because the other alternative is that e to power lambda t is equal to 0. And if e to power lambda t is 0, it means x is going to be 0, which is a trivial solution. So what if this system never moves? That's that scenario that it captures. So we are not really interested in the option of a e to lambda t being equal to 0. So that is out. So what is left is that this equation has to be equal to 0. This, guys, is called the characteristic equation. So this lambda squared plus 2 lambda plus 5 is what we call the characteristic equation, this equation. And do you see how similar this is to the original differential equation? Wherever you have a dot, a lambda appears. So double dot, lambda squared. Dot, lambda, where there is no dot, lambda doesn't appear. So that's the characteristic equation. Now, you can find roots of this characteristic equation. How? Basically, you're finding values of lambda that makes this equal to 0. So this is a second order polynomial set it equal to 0. You find the roots. You get the idea, right? Okay. Now, I want to show you that the roots of the characteristic equation are exactly the same as poles of the transfer function. Let me repeat. I want to show you that roots of the characteristic equation are exactly the same values as the poles of the transfer function. How are we going to do it? First of all, we have to find the transfer function for this system. So I'll give you 30 seconds. Find the transfer function for the differential equation that I have at the top. So what is the transfer function? Basically, I'm asking you what is x of s over u of s. We want this transfer function. So what do we do to find the transfer function? You take the differential equation, assume all initial conditions are equal to 0, and create and take it to Laplace domain. So x double dot in Laplace domain becomes s squared, x of s, plus 2s x of s plus 5x of s equals u of s. That's the transformation of the differential equation into Laplace domain, assuming all initial conditions are equal to 0. So we are ready to form the ratio. So g of s is going to be equal to 1 over s squared plus 2s plus 5. Yes? No? Do you see any mistake? Do you disagree? Okay. Now, what are the poles of this transfer function? How do you find poles? So you set the denominator, the bottom portion, equal to 0. So let's do that. So what do you need to do? You need to set s squared plus 2s plus 5 equal to 0. Now, I don't want you to find values of s. What I want you to do is to compare that equation to the characteristic equation of the differential equation. Do you see any similarity? They're exactly the same equation. So in other words, roots of the characteristic equation are exactly the same as poles of the transfer function. So it doesn't matter at which model you're looking. You can get the exact same information no matter what model you have, so far at least, between differential equation and the transfer function. The last thing we need to do is to look at the state space model. See what is the equivalent thing that we can pull out of a state space model. For that, we need to form the A matrix. You need to form the A matrix of the state space model. So if X is, as we have done it, is made of X and X dot, the A matrix would look like this. So as always, this would be 0, 1. And in order to get the second row of the A matrix, what I need to do is to write x double dot in terms of x and x dot and u. So x double dot, if you rewrite it, is going to be minus 5 times x minus 2 times x dot plus u. So can you tell me what the second row of matrix A therefore will be? So minus 5 is multiplied by x, therefore goes here, and minus 2 is multiplied by x dot, therefore goes there. We don't have to find BC. I want to show you that the equivalent to poles and roots of characteristic equation are the eigenvalues of matrix A. Eigenvalues of matrix A. So here's, if you need a refresher, the way to find eigenvalues is to form this determinant. So we are after eigenvalues of matrix A, and in order to find it, we form this determinant. We form determinant of lambda I minus A. Lambda is a scalar. I, what is I in matrix language? The identity matrix. So you take lambda and multiply it by the identity matrix and subtract from that matrix, matrix A. And you set the determinant of the resulting matrix equal to 0. So let's do that. We need a bit of space, so let's, okay. So let's form lambda I first. So this is a 2 by 2 matrix, which means lambda I is lambda. So lambda I is lambda times this matrix, 1, 0, 0, 1. This is the I matrix, which will make it lambda, 0, 0, lambda. This is lambda times I. And we have the A matrix. So let me go ahead and find now lambda I minus A. This means you just write your lambda I, so lambda 0, 0, lambda, and subtract from it matrix A, which is 0, 1, minus 5, minus 2. They're both 2 by 2 matrices, so we can subtract them, which means each member of the matrix, the first matrix gets subtracted by the corresponding member of the second matrix. So from lambda, what is subtracted? Lambda is at row 1, column 1, so we need to find what is sitting at row 1, column 2 of the second matrix and subtract it from lambda. So it's lambda minus, so it's lambda minus 0. So let's stay on row 1. The second element on row 1 is 0. So it's 0 minus what? 0 minus this element. So 0 minus 1. Row 2 is 0 minus minus 5. So it's 0 plus 5. Again, on the second row, we have lambda. So it's lambda minus minus 2. So it's lambda plus 2. So the matrix, therefore, is lambda minus 1, 5, lambda plus 2. What is this matrix? This is matrix of lambda I minus A. The next step is to find the determinant of this matrix and set it equal to 0. I forgot to mention that in order to find the eigenvalue, we need to find determinant of lambda I minus A and set it equal to 0. So let's go ahead and find the determinant. So determinant of lambda I minus A is going to be this determinant of lambda minus 1, 5, lambda plus 2. So that will give you lambda times lambda plus 2 minus minus 5, which is plus 5. So it's going to be lambda squared plus 2 lambda plus 5. And I have to set it equal to 0 in order to find the eigenvalues. This system is a second order system, so it has 2 eigenvalues. So any similarity? Look at this equation from which you can get the eigenvalues. Look here. Do you see any similarity to the equation from which you can get the poles? And to the equation from which you can get roots of the characteristic equation of the differential equation. These are essentially identical equations, which tells you what? The bottom line is, no matter what model you have, so roots of characteristic equation are the same as poles and the same as eigenvalues. This comes from differential equation model. This comes from transfer function, and this comes from the state space model. No matter what model you have, you can get these values which define the nature of the transient response. The only reason, at least at this time, we are interested in them, it is to find the nature of the transient response. So these define the nature of transient response. That is why they're important to us. Their location on the complex plane their values, in other words, will define the nature of the transient response. Okay, let's do this. Let's go back to our MATLAB. Let's go back to MATLAB and try this concept. So we are going to create second order systems with various location of poles and show you the type of response that you can get. So the standard step is to define what S is. So S is transfer function variable. So you need this equation. S is TF single quotation S. That basically tells you what S is. Okay, so let's define a transfer function G1. It's going to be equal to 1 divided by, in the denominator, I'm going to have S plus 1 times S plus 2. Now, before you hit enter, what kind of transfer function is this? What is the order of the system? Second order, very good. How many poles, therefore? How many poles are there? 2. What are the values of those poles? What values of S will make the denominator go to 0? -1, -2, very good. So this system has 2 negative poles, or this system has 2 negative eigenvalues, or this system has 2 negative roots of characteristic equation. No matter which one of these you find, you will find -1 and -2. Okay, so this system has 2 negative real poles. So what do you expect the nature of the transient response, of the step response to be look? So how will it look like, the nature of the transient response? So what we need to do probably is to go back to this picture and remind ourselves that if the poles are real and negative, of course, these are impulse responses. These are not step responses. And we are going to go and find impulse response of that system for consistency. We're not going to look at step at first, at least. So if you look at the impulse response of that system, the poles are 2, and they're located here. Do you expect to see any oscillations? No oscillations. That is our expectation. So let's go ahead and find impulse response of this system. So you need another semicolon. So type impulse of G1 and hit enter. So a sudden input to this system initially gives a rise to the output of the system, and this gradually goes down without any oscillation. Okay. Now I want you to see something that is going to be potentially interesting. There are 2 poles here. The 2 poles are located at -1 and -2. Let's keep the one that is at -1 and move the one that is at -2 farther to the left. Do you know what I mean? So instead of this being at -2, let's move it to -5 and see what happens as a result. So let's do that. So the way to do it is I'm going to define a new transfer function so I can keep this response and look at the new response. So I'm going to call that new one G2, and it's going to be equal to 1 over S plus 1, because we decided to keep the -1. But the second one is going to be S plus what, if I want a pole at -5? S plus 5. And I'm going to look at impulse of G1, comma, G2. So we are moving one of the poles to the left and see what happens. So the shape of response didn't change. The shape of the response didn't change. And the overall speed of the system didn't change either. So the same amount of time that it took the first system to go to steady state, it took the second system the exact same amount of time to go to the steady state. So in other words, the speed of response didn't significantly change. Okay? So that brings us to the concept of dominant poles. By now we know poles define the transient response. Don't we know that? I think we agree all that poles of a transfer function define the transient nature of the response. But the question becomes this. If you have more than, with one pole, we are very comfortable. With the first order system and one pole, we can quickly say, okay, this system has a pole here, therefore the speed is this. The pole now goes to the left, the system becomes faster. The pole goes further to the left, and the system becomes faster and faster. The question is this. If you have more than one pole, which one will determine the transient nature of the response? Which one would be dominating the response? So I'm going to show you, let's go back to our PowerPoint. So we are going to talk about the dominant pole or poles. So dominant pole or poles. So there is a simple rule of thumb to find what pole or poles are the dominant ones. This is the complex plane, the real axis, the imaginary axis. The rule of thumb is if you have multiple poles, so let's assume you have one pole here and another one here. And they're both real and negative. So call this P1 and call this P2. So this, so we mentioned as poles move to the left. So as poles move to the left, the speed of response becomes faster. And it's easy to see it here. Look at this plot. These two are two responses to the same input. See, this one takes a longer time to go to zero when it's compared to this one. So in other words, between P, if you call this P1 and call this P2, P2 is faster than P1. So the general rule of thumb is as you move your poles to the left, the system becomes faster. And as you move them closer to the origin, their speed gets less and less and less. Are you following me? So the poles that are closer to the origin are slower, which means the response associated with slower poles will stay around longer. So if these were two independent responses and you were to add them, this will quickly disappear while this will stay longer, right? Stay around longer. Therefore, P1 is called the dominant pole. Dominant pole because its speed is slower. It doesn't go to zero as fast as the other pole. So let me go back to my question, the question that I asked. If we have multiple poles for the same system, how the response will be determined, the transient portion? The answer is by the dominant pole or poles. By the dominant pole or poles. So that was only the case when we have real poles. So when the real poles are the only choice we have, the one that is closer to the origin would be dominant. What if we have a pair of complex conjugate? So if it's a second order system and we have a pair of complex conjugate, the same concept applies there, but with this additional twist. That a pair of complex conjugate will give you an oscillation. So there, what determines what the dominant pole is the damping ratio. The poles that have smaller damping ratio, they don't die as quickly. Do you see that? So the poles that have smaller damping ratio are going to be the dominant poles. Okay? So let me write this down. So for complex conjugate, a pair of complex conjugate poles with smaller zeta is going to be dominant or dominant. So let me give you an example. So between P1 and P2, these are real. Which one is dominant? The one that is slower. So P1 is dominant. So what does it mean to be dominant? It means the transient portion of the response is going to be determined by P1 and not by P2, because the effect of P2 quickly goes away. So, but let's look at another example. So here is our complex plane again. And let's say we have one pair of complex conjugates here and another pair of complex conjugates here. So pair 1, this is pair 1, and this is pair 2. Pair 1 and pair 2. Now which one is going to be the dominant pair? Do you remember how to find damping ratios? It had to do with sine of an angle. Which angle was that? The angle formed between the positive imaginary axis and one of the poles that are to the left of it. So which one of these two pairs will give you a larger angle? Pair 1 or pair 2? Pair 2 will give you a larger angle, which means zeta 2 is larger than zeta 1 simply by this angle. So if you draw the line, this angle, theta, this is theta 1, and this is theta 2. So theta 2 is larger than theta 1, so it means its sine is also larger than sine of theta 1, which means now zeta 2 is larger than zeta 1. Okay, knowing that, which pair is going to be the dominant pair? You said the dominant one is the one that stays longer, stays around longer. So which one of these two pairs will stay around longer? Pair 1, because pair 2 has a larger damping ratio, which means it's going to die out quicker. So again, pair 1 are dominant. Okay, Another example here. So one pair here, another pair there. So this is again, these two collectively we call them pair 1, and these two we collectively call them pair 2. Which one would be the dominant pair? If you draw the line, I wanted to put them all on the same line. So when you draw the line, they would both get the same damping ratio. Do you see that? So zeta 1, is exactly equal to zeta 2. Does it mean you can't distinguish the dominant pair? Yes, you can. You still can. If you remember, for a pair of complex conjugate, the time constant was 1 over zeta omega n, where zeta omega n is this distance. So that means that this pair have a smaller time constant, which is, this is faster. So again, pair 1 is dominant. So time constant associated with 2 is smaller than time constant associated with 1, which means pair 1, again, are the dominant. So that's the concept of dominant pole or poles. Okay, so with this, do you remember what we did here? These are two different systems. These are two different systems where their dominant pole is the same. Let me bring it up. The two systems had one pole at -1, and their second pole, one was at -2, and the other one was at -5. By now, we know that -1 pole is the dominant pole. And that is why the nature of these response in terms of transient and how fast they die out is very similar. Okay. Now, probably to make it a little bit more interesting, let me show you a third system. The third system is not even going to be a second order system. It's going to be a first order system made only of the dominant pole. So it has only one pole at -1. So let's compare these two to G3 when it has only one pole, and that is at -1. See? Even though it's a completely different system, it's a first order system, doesn't have the second pole, again, the speed of response, the nature of the transient, the fact that it dies down and it dies out at that speed is similar. So the message again is location of poles, guys. Determine the nature of their transient response. And let me again remind you of this figure. This is a very important figure. You should be very, very, very comfortable knowing what this figure shows, what the importance of each of these dimensions are, damping ratio, natural frequency, and their relationship to the transient nature of the response of the second order system. And this basically tells you that if you have multiple poles, what we just discussed, if you have multiple poles, the ones or the pair that has a smaller damping ratio is going to be the dominant pair, and the formula in the middle basically is the sine of that angle, the real part divided by the absolute value. Okay, so far, let's just review what we have done. we've been able, by having the model of the system, either of the three, we were able to find steady state response. We were also able to tell what kind of transient response we can expect a system to show. What kind of transient response we expect a system to show, and we know why poles would determine the transient portion of the response, because you remember how we tried to solve the differential equation? Do you remember? By method of undetermined coefficients. Let me remind you one more time. Maybe I didn't emphasize it enough. See, when we started solving this differential equation, we assumed this exponential response, right? And we said the roots of the characteristic equation are going to be the exponents here. And we said further that the roots of the characteristic equation are the same as poles of the system. In other words, in response of dynamic system, poles of the transfer function or eigenvalues or the roots will find themselves as the exponents in the response of the system. That is why they determine the transient nature of the response. So this is the why of it. Okay. Now that we know the response qualitatively, can we go ahead and find the actual response? And for the next 10-15 minutes, I'm going to talk about how to find response of dynamic systems, and then the rest of the class will focus on solving the sample exam. Is that okay? All right. So let's start by a transfer function. If we have a transfer function, what is the main assumption we make in order to find the transfer function? Every time we assume what? All initial conditions are equal to 0. That means when you have a transfer function, you can't find the effect of initial conditions on the response. That, by the way, is called the homogeneous response. So when you have a transfer function model, you're limited to only finding particular response, which is response to a given input. Okay. With that out of the way, if we have a transfer function, that's ratio of output over input. And if I know input in time domain, I can take my input into Laplace domain and therefore find y of s in Laplace domain. If I have y of s, I can take inverse Laplace and find response of the system. So let's. And this is just a reminder that both finding Laplace transform and finding inverse Laplace transform is done through an integrative type transformation. So this is the definition of Laplace transform. So if you have a function of time, through this integral you can find Laplace transform. And if you have f of s, through the second integral you can find inverse. But rarely do we do these integrations. Either we use tables, or MATLAB even can find Laplace and inverse Laplace. Okay, so assuming that we have these tables, one of the major steps is to find inverse Laplace of functions. So I'm going to ask you to use the table and find inverse of 1 over s plus a. What is inverse Laplace of 1 over s plus a? And inverse Laplace of 1 over s times s plus a, and inverse Laplace of 1 over s plus a times s plus b, and inverse Laplace of the last ratio, which is omega n squared over s squared over 2 zeta omega n s plus omega n squared. The method to find inverse Laplace is simply finding the Laplace transform, if it is in the table, and then the equivalent time function is next to it. So do we see 1 over s plus a anywhere? Which row is that? It's row 6. Do you see 1 over s times s plus a? Anywhere? How about row 14? So you have it. So basically, these are the inverse Laplace of these four functions. And they happen to be in the table, so it's fairly easy to find the inverse Laplace. If they're not, then you find more extensive tables, or you use a tool like a MATLAB to find inverse Laplace. Okay. Now that we know there is a time function and there's Laplace, and we can go either from time to Laplace domain or come back from Laplace domain to time domain, let's look at the use of this. The use of this in finding responses. So here it is. Let's look at this example. The example is a first order transfer function, 10 over s plus 1. Now, before finding the response, what is going to be the steady state response of this to a unit step input? Unit steady state response, how do you find it? Final value theorem, which essentially says for a unit step, set s equal to 0. So what is a steady state response? 10. What would be the nature of the transient response? What is the only pole that this system has? -1. So we expect an exponential rise. So no oscillation, because it's not complex conjugate, right? So what we expect qualitatively is this. So if I give this a unit step input, I expect it to start from 0 and go to 10 and stay there. That's my expectation. We know this so far. That's what we discussed so far. Now we are going to actually find a function for the response. So what are we going to do? We recognize that the g of s 10 over s plus 1 is y of s over u of s. If the input in time is 1t, which is a unit step input, its Laplace transform, according to the table, is going to be 1 over s. So if you look at the table of Laplace transform, it says if your time function is unit step, your Laplace transform would be 1 over s. This is the second row of this table 2, 1. Do you see that? Everybody? Okay. So we know Laplace transform of a unit step is 1 over s. So we have u of s and we have g of s, which is the ratio. From there, we can find y of s simply by multiplying. So what we are saying is y of s is equal to u of s times a ratio of y of s over u of s. That's what we are saying. So if you take your ratio and multiply it by u, you get y. And that's exactly what we are doing in this second line. So this is u of s. This is the ratio. So your y of s is now this ratio in Laplace domain, 10 over s squared plus s. Now, we want y in time domain. We want to have y in time domain. So this is y over t. This is 10. Okay? So what do we need to do? We need to find inverse Laplace of this ratio. Okay? So we need inverse Laplace of 10 over s squared plus s, which means 10 times, it's a constant, so you can pull it out. So 10 times inverse Laplace of 1 over s plus 1. And if you look at the table, inverse Laplace of this ratio is 1 minus e to power minus t, and 10 is a constant, so you get to multiply by it. So here's your challenge. Plot this equation, plot this function rather. So go ahead and plot this function versus time. So grab your pencil and plot the response, which means you need to determine what is the value of this function at time 0, and then how this function changes as time goes on. So what is the value of e to power minus t when t is equal to 0? What is e to power 0? It's 1. So at time 0, we have 10 times 1 minus 1, which is what? So at time 0, the value of function is 0. Okay. So that's settled. At time 0, the value of function is 0. Now, we want to know as time goes on, what will happen. Okay? So let's do this. Because e to power minus t is going to appear a lot of times, let's do this first. Instead of y of t, let's plot e to power minus t. What is value of e to power minus t at time 0? We decided that it was, at time 0 it was 1. So e to power 0, it's 1. How does e to power minus t look like after that? Does it go down? Does it go up? Or remain stationary? The answer is it actually goes down towards 0, and it becomes equal to 0 when time reaches infinity, which is if you wait long enough. So e to power minus t is an exponential function that goes to 0. It decays from 1 and goes to 0. Now, you are subtracting this function from 1, which means the overall response starts from 0, and when e to negative t becomes equal to 0, the remaining function becomes equal to 1. And not 1, 10 times 1. That's why the function goes to 10. So response goes from 0 to 10. Now, let me bring one more thing to your attention. Can you pay attention for a second? What was the only pole that this system had? Pole of the system? And there is no surprise that this is e to negative 1t. So the pole appears with a negative, pole is negative 1, so it appears in the exponent of the time function. So can you guess if the original transfer function was 10 over s plus 2, what would you get in the response? You would get e to power minus 2t in the response. And that would have been a faster response. The pole would have been to the left, and the system would be faster. So that was finding response from a state space system model. This is another one. Please give this a try. G of s is 10 over s plus 1. And input this time is a unit impulse input. Unit impulse input. Go ahead and find the response of this system. Because you may not have access to the table, I'm going to tell you that u of s for a unit impulse is simply 1. And u of s for a ramp input, by the way, is 1 over s squared. So what is y of s for the first case where you have a unit impulse input? Remember that g of s is y of s output over input u of s. So what is y of s equal to for the first case? And for the second case, that's where we have to start. So we have to find y of s for both cases and then find inverse Laplace. Y of s for the first case is simply the transfer function because u of s is 1. So y of s simply would be 10 over s plus 1. And from here we find y of t, which is inverse of 10 over s plus 1 to be equal to what? This was one of the examples we just solved. Let's go back. So for the case when we had 1 over s plus a, it was going to be e to power minus t. So the response is going to be 10 e to power minus t. Again, is it a surprise that you see the pole as the exponent in the response? No, that's supposed to be like that. If you saw anything else, we should go double check our solution. Okay, how does this look like? If you plot this function, what is the value of the function at time? So to call this y1 to distinguish it. So plot y1 versus time. So what is the value of this function at time 0? So e to power 0 is what? E to power 0 is 1. So value of this function at time 0 is 10. It's 10. As time goes on, what will happen to this function? It just goes to 0. So this is an impulse response, which means it's equivalent to having some initial condition in the system. So that's exponential decay. So it starts from 10 and goes to 0. That was the impulse response. Now compare that to the step response. See, the step response looks like this. Goes up with the same exponent of negative t. This one goes down with the same. Okay, you ready for the second one? Ramp input. So for ramp input, the Laplace transform is 1 over s squared. So u of s, y of s rather becomes 1 over s squared, which is u of s times 10 over s plus 1. So y of t, which is inverse of this function. Do we know what that is? Let's go up. So it's s squared times s plus a constant. It's row 19 here. So in our case, a is 1. So it's 1 over a squared, which is 1. Then at, which again is t for us, minus 1 plus e to power minus t. So it is. So the response, according to the table, is t minus 1 plus e to negative t. Did I have the signs correctly? Let me double check. So minus 1 plus e to minus 8t, which a here is 1. Again, in this response, you also see the trace of the pole of the system. So e to negative t again shows up because the pole of the system is at the same location. Now, plot this response. How will it look like? So t, y, 2. So at time 0, what is the value of the function? Plug, wherever you see t, plug 0. What will you get? T, yes?
Sorry, what happened to the 10 again?
The 10, I simply didn't, I forgot. So it should be here. So the 10 Let me put it here. So 10 should be included. Thank you for reminding. So back to my question, when t is equal to 0, what is the value of this function? For t, you have 0, you have negative 1 plus e to power 0, which is 1, minus 1 plus 1, so value of function at time 0 is 0. Okay, as time goes on, what will happen? As time goes on, we know e to negative t will go down, and it eventually becomes equal to 0. Do you agree? How about t? As time goes on, what will happen to t? Simply goes up. So what will happen is after a transient portion, the response becomes simply this. So this is a ramp input, which means the level of input keeps increasing, and so does the level of output. So eventually the response converges to t minus 1, because e to minus t will diminish over time, will go away over time. So this, in steady state, this looks like t minus 1, because the effect of e to negative t will disappear over time. And there are a number of other examples. With solution, this one does have the complete solution, so please take advantage of it. And now to a system that we know and feel quite comfortable with right now. This is a second order system, the transfer function of a second order system, where zeta is between 0 and 1. So we are dealing with an underdamped system. Our interest is in finding unit impulse response of this system. So if u of t is delta t, which means u of s is 1, what is the response? The response is u of s times g of s, and in order to find the response in time domain, we need to find inverse Laplace. Essentially, we need to find inverse Laplace of the transfer function. Whenever you're dealing with impulse type response, because u of s is always going to stay at 1, it is equivalent to finding inverse Laplace of the transfer function itself. So if you look at the table, the inverse Laplace of this function has been found. So if you look at the table, what you find as the function is this. So let's spend some time, and this is from row 22 of the table that I gave you. Let's spend some time and look closely at this function and see if the type of response that we expect from an underdamped system is there. So what do you see? You see omega n over 1 minus zeta squared. That's a constant. So each system has a natural frequency and a damping ratio. Once you know the number, that's a constant. Do you agree? Okay, let's go forward. This is e to power minus zeta omega n t. What does this function do? At time 0, what is the value of this function? What is the value of e to negative t at time 0? 1. As time goes on, what happens to this function? So this function will do this. This is e to minus zeta omega nt versus time. Do you see? So that's the job of that function. It brings the response down. How about this last one? What kind of function is that? It's a sine function. At what frequency? Frequency of omega n times square root of 1 minus zeta squared, which is called damped natural frequency, by the way. So what is this function? This function, just by itself, if you plot it, it simply will look like this. A sine wave that doesn't diminish, does it? There is nothing in the function that tells it go down in amplitude. But once you multiply these two functions, the result is what? The result is an oscillation that decays over time. Now you should see why, when damping ratio is more, the rate of decay is faster. Why? Because of this. If you have two exponential functions, so one looks like this, and the other one is slower. So this, for example, could be e to negative 2t, and this could be e to negative t. So when the absolute value of the exponent gets larger, the decay rate gets faster. And that is exactly the function of zeta. As zeta gets larger, the rate of decay gets faster. So that was unit impulse response. We can do the same thing for unit step response. Again, in that case, u of s would be 1 over s. You multiply it by the transfer function, and you will find the inverse Laplace. And inverse Laplace is captured in the tables that I included in the slides in row 24. So in row 24, what you will find is a similar function. Again, e to minus zeta omega nt would be there. Sine would be there. But see, the big difference is this 1. The big difference is this 1. So instead of the response diminishing and going to 0, this response diminishes and goes to 1. And the reason is because you have a unit step. The input is always present. In impulse, you have a quick input that goes away, but in step input, the input is present, so the response simply follows the input. So this is an exponential response, an oscillatory response that converges to 1. Why? Because e to power minus zeta t, which is this one, will go to 0 eventually. This eventually over time goes to 0, so what is left is 1 in steady state. And if, of course, if the damping is exactly equal to 1, you can repeat the process and get to a response that is completely oscillatory. And we've talked about this. So let me remind you of this figure, that as damping ratio changes, the location of poles change. So for 0, you have a pair of imaginary, and as damping ratio changes, this pair moves and eventually meet here when zeta is 1, and when zeta is larger than 1, the two poles would be here and here. This is for 1.2. So this is a composite response. So blue shows undamped when zeta is 0. So the response is simply a sine, which never decays nor it expands in response. But these are all the underdamped responses. When as zeta increases, you go from an oscillatory response to non-oscillation at all. And that's how you can find it. You can find numerical values for the response. And that's how we were able to find equations relating overshoot, for example, to damping ratio. This wasn't a magic. We knew the actual equation for the response, so we can calculate the overshoot and then relate it to our damping ratio. You remember we had an equation relating damping ratio to the level of overshoot? It came from those results. And the same way with settling time, the same way with rise time. So I'm going to show you a table. This table basically has tabulated various qualities of response for 3 important values of zeta. So on the top row, you see damping ratio of 0.5, damping ratio of roughly 0.7, and damping ratio of 1. The first two are underdamped. This last one is critically damped. And you can see that value of damping has no effect on the steady state response. Value of damping only is going to affect the transient portion of the response. And how? It's going to affect the rise time. So you can see the rise time is going to be for each level of damping as your damping increases, So does the rise time. So the rise time gets larger, so the system generally gets lower. Of course, the natural frequency here, natural frequency is shown as omega 0. The source that I got this table from shows this as omega 0. But you can see the effect of natural frequency, which is as natural frequency increases, the rise time decreases, so the system becomes faster. It has the overshoot, and you can see as damping ratio goes up, overshoot goes down. And when you have damping ratio exactly equal to 1, there is no overshoot. And the settling time also, as you go up in damping, settling time also goes down. So you can see that there is a reverse effect between rise time. Remember rise time? Let me show you this figure one more time. Rise time is this initial jump. How quickly this initial jump happens. Settling time is how quickly the system will settle. The oscillations will go away. So the effect of damping on rise time and settling time is in opposite direction. Means what? Means as damping increases, rise time goes up. So the initial response gets slower. But the overall response, the settling time, favorably change. As damping goes up, the settling time gets shorter. So these are opposing trends that we have. Okay, so the last topic that would appear on the exam is the topic of finding complete response from a state space model. So we already talked about finding response from differential equations and from transfer functions. So can we now use the state space model to find a complete response? And the answer is yes. And like what we've been doing so far is we take advantage of similarity of the state space model to first order differential equations. Because state space models are that. They're a collection of first order differential equations. So we are going to take advantage of it. So when we talk about finding response of state space systems, we essentially means if I know initial conditions, because the system has n state variables, knowing initial conditions means knowing n values at time 0. Example, mass spring damper system is a second order system. Initial conditions means I know initial position and initial velocity. That means knowing initial conditions. Now, when we say we want the response, it means that we want y as a function of time. And y has two portions, like any other differential equation. It has the homogeneous part and it has the particular part. Homogeneous is when there is no input, so u is 0. Particular, so in homogeneous you are capturing the effect of initial conditions and only initial conditions. In particular, you capture effect of the input. So let's look at each of them at a time. So this is the simplest differential equation you could have. Tx dot plus x is equal to u. I showed you the way to find this. The solution to this differential equation is to form its characteristic equation, which means assume a certain portion of the response, which we are assuming here. This is the assumed homogeneous response. And if you plug that back into the differential equation, you find lambda is going to be equal to minus 1 over t. And if you enforce the initial condition that x at time 0 is x naught, this is a known value, then you get to this equation that x homogeneous is x naught e to power minus t over capital T. So from the differential equation, basically you can find a homogeneous response. And t, by now we know it's the time constant, so the larger the t, the slower this response will be. And you can now see by seeing where the t ends up in the denominator of the exponent, the larger the t, the basically slower the response would be. So that was the homogeneous portion of the response. How do we find the particular response? We need to know what the input is. So if the input, for example, is a unit step, the differential equation becomes tx dot plus x equals 1. So how do we find x particular, the same way. We make an assumption that x particular is c e to power lambda t with this difference that previously we assumed c to be a constant. When we found the homogeneous, we made the assumption that c was a constant, and we found that constant to be equal to initial condition. In finding particular response, we don't assume c to be constant. Rather, we let c be a function of time. So we can capture the effect of any input we want. So if you make that assumption that c is a function of time, you can, similar to what we did in the past, you can find x dot and plug it into this equation. So let's go ahead and together find x dot. So if x particular is this, if you want to find the time derivative of this is a multiplication of two time function. It would be c dot times e to power t over capital T minus c times derivative of this, which is minus 1 t e to power t over t. So this basically together is time derivative of xp. Why are we finding this? Because we need to plug it into the differential equation. So for x, we already have the equation. So if you bring all of these together, you will find is eventually an equation for c dot t. So you find an equation for c dot t. And in order to find c of t, which is necessary to find the actual response, you need to integrate c dot t. So if we integrate c dot t, we find this function. And again, it's no surprise that we get the exact same form as we got for the homogeneous response. Now, the complete response is the addition of homogeneous and particular response. So if you put them together, you find this form of response. So at time 0, what is the value of this function? So if you plug, lowercase is time. So if you set time equals 0, what is value of x at time 0? E to power 0 is equal to what? 1. So it's 1. So the answer is 1 plus x naught minus 1. So the value of the function, as you expect at time 0, is equal to its initial condition. That's a check to see that what we found basically makes sense. It should give you x naught at time 0. Okay, so that's that. And what is the steady state response? So if you let time passes long enough, by the way, there is a negative sign. So this is, if I want to write it, it's minus t over capital T, but it's connected to the fraction sign. So it's e to power minus t over t. So if you let time passes enough, so time goes to infinity. So if time goes to infinity, what is x steady state? So what happens to e to power negative t if time goes by long enough? It goes to 0, correct? So it becomes 1 plus 0 times x naught minus 1, which is equal to 1. So what are we saying? We are saying we already knew that the unit step response of this system was this. So from x naught to 1 has x steady state. We already knew that. Based on the location of the pole, it has one pole at -1. So we already knew that nature of the response. Now you have an equation to support what we qualitatively know. So we found the solution for the differential equation, and from the solution you can actually plot the response. And you can apply the same concept now to our state space model. Because again, the similarities are there. So a state space model is a collection of first order differential equations. So we can apply the same concept to our state space model. So we can bring into the solution the fact that x of t would be e to power at x naught, when a of t a is the root of the characteristic equation. Now this was when we have a scalar equation. Now when this becomes a matrix, so when x dot becomes ax, there is no difference. Again, we have the matrix as the exponent. Now the small problem is we know how to find e to power of numbers. You just grab a calculator, you find exp of 5. But how do you find exp of a matrix? So if you have a 2 by 2 matrix, what is exp of that matrix? The answer is there is a function that MATLAB has and some calculators have. But what that function really does, it finds this expansion, this series expansion. The expansion says if you want e to power matrix M, this is equal to this series. The series starts with what? What is I? Identity matrix plus the matrix itself. Remember, we are trying to find e to power M. So you add to identity matrix the matrix M plus 1 over 2 factorial M squared. What is M squared? M is matrix M multiplied by itself. Plus 1/3 3 factorial M to power 3, and this continues forever. Is it a good news that your series continues forever? How are you going to calculate e to power a function if this keeps going and going and going? The answer is, for most matrices, this series will stop somewhere. So m to one of the powers become equal to 0, and therefore all the higher powers of m become and stay equal to 0. Therefore, the series stops and converges essentially. So you can find exp of function. So this basically, once we have x of t, we can find y of t by pre-multiplying x by c. So this is, by the way, the homogeneous response. We haven't included the effect of input yet. So c e to power at x naught is the initial condition response. So let's go ahead and solve an example. So we want to find motion of a mass. Motion is x of t without friction and without a forcing function. So there is no friction, there is no forcing function. So if there was a differential, so what are we talking about? This is a mass, m. Its position is shown with variable x of t. And their initial conditions. So x at time 0 is x naught, and x dot at time 0 is x dot naught. So the question is, what is x of t? What is x as a function of time? What is the displacement as a function of time? Is if the only thing that causes any motion are these two initial conditions, initial position and initial velocity. So what we need is matrix A, so matrix A. But before writing matrix A, we need to know the differential equation. So differential equation, the basic differential equation, if there was an F, which here we don't have it, but just for simplicity, let's assume there is a force F. If there was a force F, mx double dot would have been equal to F. Don't you agree? There is no other force. This is a mass just by itself. It's not connected to a spring. It's not connected to a damper. There is no friction. So mx double dot would have been equal to F. Now there is no F. There is no F, which means what? So F is 0. This means mx double dot is equal to 0. which in turn gives you these matrices. So matrix A is 0, 1. It's the usual. We're basically saying derivative of the first member of X is equal to the second member of X. And B also the same way, 0, 1, and C is 1, 0 to signify that the output of the system is the displacement. So we have the three matrices. Remember, according to what we found, Y homogeneous, let's look at the equation one more time together. Y homogeneous is C e to power AT times X naught. So it's C e to power AT X naught, when X naught is a vector of initial conditions. So in this case, we have two initial conditions, one initial position and one initial velocity. In other words, X naught is made of x1 at time 0 and x2 at time 0. The first one is displacement, and the second one is velocity. Okay, so I know what C is. So C is known. And also I know what X naught is. What I need to find is e to power AT. Where I have A, I don't yet know what e to power AT is going to be. Okay? So let me remind you of the series one more time before we go any further. So this series said e to power m, look at the bottom of this slide please, e to power m is equal to the identity matrix plus the matrix plus 1 over 2 factorial matrix to power 2, and this continues. So let's go ahead and apply this to our problem. So our matrix is AT. So if A is this, AT would be what? AT would be 0, T, 0, 0. The only non-zero element that we have is 1, so that gets multiplied by T. Do you see that? Okay, so in order to find e to power AT, I need to start by the identity matrix. It's 1, 0, 0, 1, plus the matrix itself, which is 0, 1, 0, 1, T. And the good news is that that series stops right there. Why? Because if you find A squared T squared, in order to find it, you take the matrix and multiply it by itself. This is a 2 by 2 matrix multiplied by a 2 by 2 matrix, so the result has to also be 2 by 2. So let's take row 1, which is 0t, and multiply it by the first column of the second matrix. What is the answer? 0 times 0 plus t times 0. The answer is 0. Row 1, column 2, you take this row and multiply it by this column. So 0 gets multiplied by t, and t gets multiplied by 0. So the answer is 0. Row 2, 0, 0, 0, 0, easy. 0, 0, t 0, again easy. So this tells you that power 2 of matrix is 0. What is power 3 of the matrix? Has to be 0, because power 3 is the matrix multiplied by power 2. So what is power 4 of the matrix? So all remains 0. So we stop at the first. So we just stop here. So we take the identity matrix and add it to the matrix. So the result is 1t, 0, 1. So this is what? This is e to power AT. Now I take c multiplied by this and multiplied by my x naught as a vector. So let's go ahead and make this multiplication. This is 1 by 2 multiplied by 2 by 2. So the result is 1 by 2. So this is 1, 0 multiplied by 0, you get 1. 1, 0 multiplied by t1, you get t. So this is the result of the first two matrices multiplied by each other. Then you take this and multiply it by x naught. So 1 gets multiplied by x naught, so the result is x naught, plus t gets multiplied by the second one, so t x2 naught. So remember, x1 is position at time 0, and x2 is velocity at time 0. So this, what story does this line tell? It tells you y as a function of time, which is displacement as a function of time, is equal to initial displacement plus initial velocity times time. So this is x naught plus v times time, which is a very familiar formula. You have seen this before. So you are basically saying if there is no force applied and there is an initial velocity and an initial displacement, the system keeps moving at that constant velocity forever because there is nothing to slow it down. And you are basically finding it from the state space model. Then the question becomes, what if we have a non-zero input? So the previous y was homogeneous y, in absence of any input. In absence of any input. If we bring input, how do we take that into account? And the answer is exactly like what we did for a single differential equation. We make the assumption that x of t is e to power t, c of t, where c of t is a function of time. And we go through the derivation, and we find this integral, which is called the convolution integral. You may have seen it in differential equation and in vibration. Basically, what we are saying is you need to still find e to power at. That's there. You need to find e to power at through that expansion. This is x naught, which is a vector. Then you need so these two together were the homogeneous x. On top, you need to calculate this integral. Again, this is through the expansion, the series expansion. B is known, u of t is known. So if you carry this integration, you find x particular. Once you have x homogeneous and x particular, you pre-multiply it by c. So you get your y. So y would be c e to power at x naught. This is very familiar. We have already found yh. Then this would be y particular. So through this calculation. And I have a solved example. So please, this is the exact same example that we solved. This time, instead of having no force, we do have a force. So there is a force. So we are trying to find homogeneous and particular response. And the solution is included here. Please study that on your own. Now, what I owe you, so this ends basically here. This ends at slide 170. What I owe you is a solution and explanation on the solution of the sample test that I posted. Because I didn't get to do it during the class, what I will do is I will record my solution. So instead of just giving a solution, I'll do it like what I do in the class. So I will talk over my solution and I'll post it. I'll post a video of solving the sample exam. So you have a tutorial. Does that make sense? Yes, sir.
Do you consider moving the exam to Thursday?
I'm open to it. However, I announced it ahead of time, and I know some folks are out of town. So they probably made an arrangement to come to town. So it would be probably difficult for them to move things around. So out of respect for them, I would like to keep it on Tuesday. So it's like a contract. So I also posted these dates at the beginning of the class. So I'm going to, as soon as possible, post this to give you a bit more material to study. Is there anything that you don't feel comfortable at this time? I know these last few slides are very recent, so you need to study them. But other than that, if there's anything in general that needs further explanation, let me know, and I'll post this as a separate video. Thank you.